And next speaker is Boris Safonov, and we keep on RW Auriga, but expanded RY Tauri.
Hello. Just a moment. Okay, hello. I will continue to speak on RW Auriga A, but some general words before. We know that the increase of polarization during fading is a characteristic feature of UX-ORI variables, and this model actually this happens because the scattered and polarized radiation of circumstellar matter, which is here, its contribution increases while the unpolarized flux from the star decreases due to obscuration by local dust cloud. This model explains well the majority of data, but as always, there are some interesting exceptions, and I would like to discuss two of them, RW Auriga A and RY Tauri. So in case of RW Auriga A, we see that indeed polarization rises during fading and it reaches high values, but I would like to draw your attention to this beginning of this curve, which is already very puzzling, because we have really low circumstellar extinction here, around 0.7 magnitudes, and already we have very high polarization of 5%. I have to note that for example, models which Sergei Shulman presented yesterday predict that at such extinction, the expected polarization is no more than 2, sometimes 3%. So 5% is really a lot, actually. And it is interesting to try to understand what is the origin of this high polarization, and in order to do this, it would be great to actually locate it. And in order to do this, we observed the object using differential speckle polarimetry method, which allows to reconstruct image in polarized flux at diffraction limited resolution, which is in our case 50 milliarc seconds. And we don't use coronographic mask, we don't have saturation effects, and because of this, we can observe, we can detect and characterize polarized flux, which is collocated with the star. So we have this inner working angle problem, which is present in coronographs. And you see that the polarized, there is resolved polarized structure which is displaced towards blue jet, and it is roughly qualitatively consistent with the dust-wind model. So there is something above the protoplanetary disk, and we actually see it. But a lot of polarized flux is generated here in unresolved region around the star. So for this date, for the 22nd of October 2016, we know that the extinction was 0.7 magnitudes. The total polarization was 5%, and we know something about the geometry of the resolved polarized flux. We tried to model these observations by Monte Carlo radiation transfer modeling, and we started with the thin disk, and thin disk would produce just little polarized flux, and we would not be able to detect it because thin disk is illuminated very poorly, actually. It is very faint. The total polarization, the expected total polarization is small. The optical thickness along the line of sight, this is line of sight, here's the star, is negligible. So we need something to absorb stellar radiation and to generate some polarized light. And we assume that this is a second component of this circumstellar envelope, geometrically thick disk, but optically thin. So the optical thickness along this line of sight is around 2 or probably 3, something around this. We varied the parameters of this disk to approximate the observational data. And here is the best model which we managed to obtain. And it gives really high total polarization, but it requires a lot of scattering material, and because of this, the magnitude drop of the whole object is 2.5 magnitudes. So the object have to be much fainter than we actually see it. As an alternative model, we considered conical wind, which is depicted here, the section of density. And in this case, the extended structure is reproduced, and total polarization is small, and optical thickness along the line of sight is reproduced. In order to explain the data, we assumed that additional polarized flux is generated by dichroic absorption on circumstellar dust here in this structure, and this makes the star a point-like source of polarized radiation, and this model explains the whole set of observational data, the optical thickness, the polarization, and the extended polarized structure. And I'd like to pay attention to that the characteristic size of this cone we obtained is quite big, around 5 astronomical units, and it is constrained by the angular size of the extended structure which we see. So now I would like to go to the next target, RY Tauri. So this is also a UX Ori variable, and it demonstrates some chaotic changes in polarization and magnitude and brightness. And recently, its protoplanetary disk was imaged by ALMA, and the direction of the approaching jet is this. So this here is the approaching jet. This object has very prominent jet. Probably there should be some scattering material to generate polarization, and indeed it was detected using Haiqiao at Subaru, which is coronagraph, and two features were detected, which are actually which were interpreted by the Takami as geometrically thick but optically thin structure above the disk. Here's the contour plot of the data obtained using differential speckle polarimetry in I band, and we see that again there is some extended structure to the two extended structures here and here at the same position angles as in case of Haiqiao observations. And please note that this dashed line corresponds to coronographic mask. So in other words, we see much brighter and closer to the star regions of these features, but unfortunately we don't see fainter and larger part of them. And again, we don't use coronographic mask, so we are able to characterize polarized source which are collocated with the star. And just a moment, in the model of the in the model of generation of polarization of UX or variables by scattering, one can expect that the polarized flux structure, the nebula in polarized flux should be some more or less stable, and the majority of variability is due to variable brightness of the unpolarized star. In case of RY Tauri, we can see something completely opposite. Here are the images of this object in polarized light at several epochs, and the interstellar polarization was subtracted. And we can see that it actually consists of two components. There is two extended features which are present on each dates, note different brightness scales. But this point-like source, unresolved source, which is collocated with the star. Its polarized flux is all the time. It is changing. And sometimes the polarization can change on the time scales of weeks. Note that on the 3rd of December 2018, it was faint. The extended structure was prominent, but just a week before, it was very prominent. This point-like source. And we. In order to further test this suggestion, we tried to model the data for the 25th of November by the data of the 3rd of December by adding a point-like source of polarized radiation, and this modeling is quite successful. Here's the polarization of this point-like source, and here's the displacement of this point-like source from the star. And it is less than 2 milliarc seconds. But please note that we don't resolve this point-like source, so we can tell just that it is smaller than 15 milliarc seconds. I don't claim that it is smaller. I can claim only that it is not bigger than 50 milliarc seconds. Of course, in order to correctly interpret this data, we need Monte Carlo radiation transfer modeling of this source. But please remember that it is not so actually easy to get a polarization of 3%, while the drop in magnitude is just 0.5 magnitudes. And in case of this object, you have to do this in less than a week. At the moment, we can tell just that it is very suspicious, and probably it can be explained by dichroic absorption of direct stellar radiation on aligned dust. And I come to conclusions. The resolved polarimetric data for W Riga A are difficult to explain by scattering. The additional polarized flux generated by dichroic absorption would help. And in case of RY Tauri, the circumstellar nebula consists of two components: the stable extended component and variable unresolved point-like component, which is less than 50 milliarc seconds in size, which is collocated with the star. As the final remark, I would like to tell that there is from the observational point of view, there is a gap between photometric observations of UXOR variables and coronagraphic observations of UXOR variables. We have very dense, very rich photometric light curves of these data, of the stars. But the coronagraphic data exist only for some specific dates. And it would be interesting actually to combine these two approaches to have high resolution images of these objects taken at some, how to say, several epochs, several close epochs, and this data would probably allow us to tell something about where the polarized flux is actually generated. Okay, thank you.
All the data you are showing in one band.
Yes, it's I-band.
And do observations in other bands, simultaneous observation exist?
We also observed in V and R bands.
All your data.
Just to clarify, in case of RY Tauri, yes, we have VRI observations quasi-simultaneous, because one observation takes about 10 minutes. And in case of RW Riga A, it is R and V bands.
When you analyze by this way, other bands, result is the same?
You mean for RW Riga? Yes, we took into account both V and R bands.
When you model?
Yes, when we reproduced the observational data, we considered both V and R bands.
Antonella.
What kind of dust model are you using? Have you played with that to see if it
yes, we have. Unfortunately, we weren't able to reproduce the data with compact dust. You know that there are models of porous dust these days, and porous dust generates more polarization during scattering, and we managed to reproduce the data only using porous dust, and size distribution was interstellar from 5 nanometers to 150 nanometers. So it is small and porous, yes, but it's actually quite expected, because when the dust is entrained by the wind, it is more likely to entrain porous dust, because it's fluffy. Yes, it's less.
How much porosity? What is the porosity?
60%. 60%, not so big.
It is well known that there are several young objects which have very large linear polarization. Many years ago, this polarization was explained by aligned grains, as in this case. Nevertheless, now it is clear that there is a simpler mechanism which explains the same high linear polarization. When we screen the star and if we observe the jet, in such a case we will have very high linear polarization. Therefore, it is not very clear for me the importance of the additional mechanism by aligning grains in this case.
Yes, it's possible to get high polarization when your object is very faint, because this geometry, the scattering by jet, for example, the jet cannot scatter a lot of light. It scatters very little amount of radiation, because it is seen from the star at the small solid angle. And actually, you cannot, if you want to get high polarization from the object, high total polarization, you have to assume that the object became fainter and fainter. So you cannot just get arbitrarily high polarization by scattering, because the scattering material starts to obscure the whole object. And for example, in case of RW Riga A, we have 30% polarization, but when the object is 100 times fainter than during pre-eclipse state. And surely this model explains the majority of data, but the sometimes interesting things happens for exceptional objects. For example, these two ones. Because okay, I will finish with that.
A little bit on the same line. So if I understood it correctly, the uniqueness was it's a single observation where it's 5% polarization at the state when it's bright.
No. We have we have whole polarization magnitude curve.
Yes, but this one point was exceptional, wasn't it? For RV Auriga.
Yes, I see a point. Yes, but actually there are some other points which are not very far. Here, some. Yes.
But then
these ones.
But you need then the mechanism to set in at certain date. But then certain other periods it's gone.
Yes, it's one of the next steps. It's actually to reproduce temporal behavior of this object, but it is much more complex because it will require more assumptions. Because of this, we wanted to focus on this particular date. Well, there are some other points with high polarization nearby.
Points around 0, I think.
Yes.
Yeah.
This is before eclipse state. This is before 2010. It is important.
Okay, so when it was really quiet.
Yes, when there was no dust wind, and it is interesting also that the polarization angle before 2010 was almost random. It was around 100 degrees, and after during eclipses it was extremely stable and parallel to the disk, which conforms to the wind hypothesis.
Any other questions? If not, let's thank the speaker again. Do we have local announcements? If not, then lunch break and back 2:30. Thank you.